Welcome to our podcast. Today, we're diving into time series econometrics. This field is essential for understanding economic data that unfolds over time, like GDP growth or inflation rates. Our goal is to make sense of these sequential patterns and relationships.
Time series econometrics sounds quite specialized. Could you start by explaining what a time series actually is in this context?
Absolutely, a time series is a sequence of data points ordered by time. We often model these as realizations of underlying stochastic processes, which are systems evolving randomly over time. A key concept is stationarity, meaning the statistical properties like mean and variance don't change over time.
So, stationarity means the data behaves consistently over time. What happens if it doesn't?
Exactly, if the mean, variance, or other statistical properties change over time, the series is non-stationary. Many economic series, like stock prices or GDP, are non-stationary. This can lead to problems like spurious regressions, where unrelated variables appear correlated.
Spurious regressions? That sounds like a serious issue. How do economists typically deal with non-stationary data then?
The most common approach is transformation to achieve stationarity. A primary technique is differencing, where we calculate the change between consecutive observations. For example, looking at the change in GDP from one quarter to the next often yields a stationary series.
So, differencing helps remove trends and seasonality. What are some common models used once we have stationary or near stationary data?
We often encounter models like the random walk, which is a fundamental non-stationary process. Then there are moving average MA models, which use past forecast errors, and autoregressive AR models, which use past values of the series itself. These capture different types of temporal dependencies.
A random walk sounds like it just wanders unpredictably. Is it always non-stationary?
Typically, yes, a standard random walk is non-stationary. For data that might still have some non-stationary characteristics or complex dependencies, we use ARIMA models. ARIMA stands for Autoregressive Integrated Moving Average, combining AR, MA, and differencing, the I for integrated components.
ARIMA sounds like a versatile model. How do we formally check if a series is stationary or non-stationary before or after applying these models?
We can visually inspect its time series plot for trends or patterns. More formally, we use the autocorrelation function, or ACF, which measures how correlated a series is with its past values at different lags. A slowly decaying ACF often signals non-stationarity.
And what does the ACF look like for a stationary series versus a non-stationary one?
For a stationary series, the ACF typically drops to zero quickly. For a non-stationary series, it decays very slowly, indicating strong persistence. Formal tests like the Dickey-Fuller test specifically check for a unit root, a common feature of non-stationary processes like random walks, to confirm this.
So, the unit root test confirms if we need to difference the data. What if we have multiple non-stationary series that seem to be related in the long run?
That leads to an important distinction: different stationary versus trend stationary processes. A different stationary process, like a random walk, becomes stationary after differencing. A trend stationary process has a deterministic trend that can be removed, leaving a stationary series.
That's a helpful distinction. So, one needs differencing, the other needs trend removal. What if multiple non-stationary series share a long-run relationship?
That's where the concept of cointegration becomes vital. If two or more non-stationary series share a stable, long-run equilibrium relationship, they are cointegrated. Even though they wander individually, their linear combination tends to stay stable, indicating they move together in the long run.
So, they move together in the long run, even if they drift apart in the short term? How do we model this long-run relationship and the short-term adjustments?
We use error correction models, or ECMs. An ECM incorporates both the long-run cointegrating relationship and the short-run dynamics. It shows how deviations from the long-run equilibrium are corrected over time, guiding the series back towards their stable relationship.
That sounds like it captures both the trend and the adjustments. What about checking if one variable's past movements help predict another's future movements?
For that, we use the Granger causality test. It examines whether past values of one time series are statistically significant predictors of future values of another. It's about predictive power, not necessarily true cause and effect, but it's a key tool in time series analysis.
So, if past money supply helps predict future GDP, Granger causality might indicate a link. What if we want to analyze the interactions among many variables simultaneously?
That's the domain of vector autoregression, or VAR. VAR models extend single equation models to systems of multiple time series, capturing complex interdependencies. They are powerful tools for analyzing dynamic relationships in multivariate economic systems, often using impulse response functions to understand shock